This is a lesson on ideal operational amplifiers, also known as op-amps, that are used in feedback mode. Op-amps are an important element in circuit design. They can be purchased in many forms, including integrated circuit form. So the purpose of this lesson is to help us understand how an op-amp works in an ideal setting, so that we can then build on that later and understand how real op-amps differ from ideal ones. So an op-amp has two inputs and one output. The two inputs are called the inverting input and the non-inverting input, often marked in minus and in plus, or sometimes just minus in plus. The symbol for an op-amp is a triangle, so you'll have always a wire coming in for each of the inputs. We have one output, and then there will also be other connections on the op-amp itself for things like the external power supply. I'm putting that in here now because I don't want you to think that the op-amp is a standalone device. It does require external power source, but those often are not illustrated in an actual circuit diagram. So here are the four characteristics of ideal op-amps. First is that they have infinite input impedance. That means that the op-amp doesn't draw any current or power from the input signal source. So it doesn't matter how small your signal is, an ideal op-amp will still be able to handle that. The second characteristic of an ideal op-amp is that it has zero output impedance, which means that your circuit will not be limited by the amount of power that can be put out by the op-amp. The third characteristic is that the op-amp itself has infinite voltage gain. That means that in practice, the amplification of a circuit will be determined by the other circuit elements, in particular a feedback loop, which I will explain later. Okay, that the op-amp itself will have infinite voltage gain. We will choose the voltage gain of our circuit by how we connect the op-amp to other things. And then finally, when we use negative feedback, which again I will explain later, the op-amp internal circuitry will act to make the inverting input and the non-inverting input equal in voltage. So I understand that by themselves, these four characteristics are not very illustrative in understanding what an op-amp does. So let's look at an example. This is a circuit using an op-amp. We have an input voltage that is connected to a resistor R1. That resistor is connected to the inverting input of the op-amp. Then we have the non-inverting input of the op-amp connected to ground. The output of the op-amp will be the output of our circuit. And then we have this resistor R2, which connects the output voltage to the inverting input. That's what we call feedback. Whenever you connect the output of something back to its input, you call that feedback. So R2 in this case is the feedback resistor. So now I'm going to show you how we apply those four rules that we just talked about of ideal op-amps to figure out how this circuit is going to behave. In particular, we want to find V out as a function of V in. Okay. So the first rule that we're going to apply is actually the fourth one that I listed. That op-amp internal circuitry, in the case when we have a negative feedback loop, acts to make the two input terminals have the same potential or be at the same voltage. Okay, and we do have R2 as a negative feedback resistor, so that means the two input terminals of the op-amp will have the same potential. How does that help us? Well, the positive or non-inverting input of the op-amp is connected to ground, 0 volts in other words. That means by rule 4 The non-inverting input, or the inverting input, has the same potential. So the potential right there is also 0, since the op-amp internal circuitry makes that potential equal to the potential of the other input. That tells us what the voltage drop is across resistor R1, because we've got Vin, our input voltage, on one side of R1, and we have V equals 0, 0 potential, on the other side of R1. So by definition, the voltage drop across resistor 1 is Vin minus 0, which is just the input voltage of our overall circuit. So that allows me to determine the current through resistor 1 using Ohm's law. The current through resistor 1 is going to be the input voltage divided by the value of R1. So I have I1 equals Vn over R1. Now we'll apply another one of the rules of op-amps. Rule 1, the infinite input impedance. That tells us that the op-amp doesn't draw any current from our signal source. Now, it's just the op-amp itself that doesn't draw any current from the signal source. It doesn't mean that our circuit as a whole doesn't draw current. In fact, our circuit as a whole right now is drawing a current I1 from our input source. But the op-amp itself is not going to use or to accept any of that current. The current that I have labeled I3 in this drawing that's going into the inverting input must be 0 according to that rule, Rule 1. In turn, that means that all of that current I1 must be going through resistor 2. In other words, I2, the current through resistor 2, must equal I1, the current through resistor 1. Now, we apply Ohm's law again. Since I know the current going through R2, I can use Ohm's law to figure out the voltage drop across R2. That voltage drop will be the current, I1, times the resistance of R2, just R2. So remember, we already decided using Rule 4 that the potential on the left side of R2 is equal to 0. So if its voltage drop is I1 times R2, and the voltage on the left is 0, then the voltage on the right of R2 must be 0 minus the voltage drop across R2, which is 0 minus I1 times R2 from Ohm's law. But that wire is connected to V out, the output voltage. That means I know V out now. V out is equal to minus I1 times R2. So, using the expression that we found earlier for I1 in terms of Vin, I have V out is equal to minus I1 times R2. Plugging in for I1, we get that that is equal to minus the input voltage over R1, all times R2. So that's what we set out to accomplish. We were trying to find V out as a function of V in, and applying the rules for ideal op-amps and Ohm's law, we've done that. We get the final result is that the output voltage is equal to minus the input voltage times the ratio of R2 to R1. Now, because the output voltage is always going to have the opposite sign from the input voltage, we call this circuit that I have used as an example an inverting amplifier, because it will invert the signal from positive to negative or from negative to positive. If R2 and R1 are different, it will also amplify the signal in addition to inverting it. So you can use this as an amplifier with a voltage gain of minus R2 over R1. If you want your output voltage to be bigger than your input voltage, you choose R2 to be bigger than R1. As an example, if we picked R2 as 100 ohms and R1 as 10 ohms, then we would have a voltage gain of 10. Okay, now an alert, just like I said at the beginning of the lesson, don't forget the external power supply. Okay, even for an ideal op-amp, the output voltage can't be greater than the external power supply voltage or less than the negative external power supply voltage. What that means is if I had, say, a 10 volt external power supply and I put in an input voltage of 2 volts to an amplifier that had a gain of 10, then you would think, well, 2 times 10, that's 20 volts. My output voltage will be 20 volts, except the external power supply is only 10 volts. So no, the output voltage would be 10 volts if your op-amp was ideal. So that's the end of this lesson, and one example to help you understand how to apply the rules of ideal op-amps. You'll want to see other examples in order to completely understand how it works, but this will at least give you a place to get started.